Electronics are made from logic gates, and logic gates are made from transistors. A transistor is a device that can be made to behave like a switch. When a switch closes, it causes the two different parts of a circuit that it connects to be at the same voltage. When a switch opens, it prevents any current from passing through. When there is no current flowing through a light bulb, both sides of the light bulb are at the same voltage. The end of the light bulb that is connected to the battery will always be at the voltage set by the battery. The other end of the light bulb will be either at the voltage set by the battery or at 0 volts, depending on whether the switch is open or closed. The same thing is true of a device which we call a resistor. If we replace the light bulb with a resistor, it will behave the same way. Suppose we also replace the switch with a device called a field effect transistor. This transistor has 3 terminals, which we will call gate, source, and drain. The terminals which we called source and drain go where the terminals of the switch used to be. So far, we have not yet connected the gate terminal to the rest of the circuit. If we apply a voltage to the gate terminal, the voltage that will exist between the gate and the source will determine whether the transistor behaves like an open switch, a closed switch, or something in between. If the transistor behaves as something in between a closed switch and an open switch, the transistor can be used as an amplifier. Small changes in the voltage on the gate terminal will create much larger changes in voltage on the drain terminal. However, in our case, the voltage that we will place at the gate terminal of the transistor will always be just one of 2 values. Either this voltage will be the same as the voltage of the battery, or it will be at 0. With this particular type of field effect transistor, if the voltage between the gate and the source is at the voltage of the battery, the transistor will behave like a closed switch. If the voltage between the gate and the source is 0, then the transistor will behave like an open switch. Let us call this part of the circuit the input, and let us call this other part of the circuit the output. When a part of the circuit is at 0 volts, we will say that it is at logic low. When a part of the circuit is at the voltage of the battery, we will say that it is at logic high. We have now made our first logic gate. When the input of our circuit is logic low, the output of our circuit is logic high. When the input of our circuit is logic high, the output of our circuit is logic low. This is the definition of a not logic gate, where the output is always the opposite of the input. To make a more complicated logic gate, let us consider a circuit with two switches. In this case, if either one of these switches closes, the part of the circuit that we call the output will be at 0 volts. The part of the circuit that we call the output will be at the voltage of the battery only if both switches are open. Suppose we implement this circuit with the same type of field effect transistor that we used before. In this case, we now have two inputs to our circuit, which are the two gate terminals of the two transistors. In this case, if either the first input or the second input is at logic high, then the output will be at logic low. This is what we refer to as a NOR logic gate. Suppose that on the output of this NOR logic gate, we add the NOT logic gate that we created earlier. Now, if either the first input or the second input is at logic high, then the output will be at logic high. This is what we refer to as an OR logic gate. We call this an OR logic gate because to generate a logic high output, either the first input or the second input needs to be high. Suppose that we instead take the NOR gate that we created earlier, and rather than adding a NOT gate to the output, we instead add a NOT gate to each of the two inputs. Now, if either the first input or the second input is at logic low, then the output will be at logic low. The output will be at logic high only if the first input and the second input are both logic high. We therefore call this an AND logic gate. If we add a NOT gate to the output of the AND logic gate, then it becomes what we call a NAND logic gate. We can also use logic gates to create an XOR logic gate. In the case of an XOR logic gate, the output will be high if one of the inputs is high, but not both. We can also use logic gates to create memory. As an extremely primitive example, consider an OR logic gate with the output tied to one of the inputs. Suppose we start out with both the inputs and the output at logic low. If we send a logic high into the free input of the OR gate, then the output will go to logic high, since the output is high if either one of the inputs is high. The other input of the OR gate will then also go to logic high, since it is connected to the output. If we now removed the logic high to the free input of the OR gate, and change it to a logic low, the output of the OR gate will stay high, due to the fact that its other input is at logic high. And the logic high output of the OR gate will perpetuate the logic high of this other input. Therefore, in this case, once the free input to the logic gate goes to logic high, the circuit will remember this, and then the output will stay at logic high forever. More information about electric circuits is